Sorry, I have been talking like 5 minutes, and then no one actually hear me. But anyway, so let's start over then. So you guys can hear me okay now, right? Yes. Okay, I have been talking for 5 minutes. So before we start, actually I was asking, do you have any questions regarding homework 1 all the way to homework 3? Um, if you have questions, go ahead and ask. And even regarding the homework or anything that logistics-wise, if you have questions, you can go ahead and ask. Hold on to that question. Go ahead. You can just go ahead and ask that question. Are we required to show any graphs? Depends. Of course, it would be helpful if we have any graphs that plot it out. Better to use R. Of course, occasionally some students actually submit a solution to Excel. At the beginning of the semester, I don't mind as much, but if after third week or fourth week you're still using Excel, that's probably not acceptable. I encourage you to use R because this is not the first semester that you started using R, and hopefully even though you didn't use it previously, then in this course you should definitely use it. Does that answer your question? Okay, I assume that's a yes. What I'm asking is we have to show our graphs. Yes, for your homework, right? Only if the question requires. It depends, right? It really, if the graph can help you to explain the problem much better, why not? So I would say that if majority of the time, actually, in those homeworks, a graph would help you to explain the question much better. So maybe I can show you one example. But, I'm trying to find out. So let's take a look at this homework 3 solution rather quickly, right? So I don't want to go through this at the moment. I probably want to go through after I grade all the homeworks, which should happen this week. For the first three, I'm going to grade 2 out of those 3, or potentially could be 1 out of those 3. And then the rest of the other 2, I'm going to post the solutions, and you have to read them yourself. And then going forward, I'm going to post the solution I'm going to grade the homework in a couple of days after your submission. So after Sunday, and then after a couple of days after that Sunday submission, I'm going to post the solution or grade the homework, give you comments. So in this case, for example, let's look at some examples. You don't really see a need for graph, but for this one, say you can see that with the graph, it's better to explain what we're trying to do. And then, of course, I want to really see some comments. Right? As I mentioned in the beginning, what do you get, and then what's the function form, and what's the best or minimum possible deviation, etc. from the graph. And then x versus y plot along with a fitted line, scatter plots with the line, and then in his case, right, the predicted value versus the original actual value. So here just give you the residual, how to evaluate how good the residual is. In this nature, I really want you to have some sort of graphics that could help you to explain the problem. Okay, and then I'm going to post all these homeworks, and then apparently if you're not following some of this format for now yet, definitely try to follow them for the rest of the semester, meaning that try to be more comprehensive, explain the problem, trying to the code, and at the end give me some comments here. For example, coefficient is whatever, and then why do you think that's reasonable solution? The solution is not using what, or how do you solve it, etc. Right. So that's give you an example. So any other questions on this? No. Okay. Just as I mentioned, I'm going to grade the first 3 homeworks, one or two out of the 3 this week, and then post the solutions by end of this week. And then next week, starting from next week, I'll be more rigorously to follow the submission of the homework, and then so that we are on the same page. So once I give you feedback, either I grade your homework or I post the solutions, you should read them on your own to understand the whole process. I think that's definitely a reinforcement for your learning, and it would be really helpful for you to understand the concepts better. And then, so let's, without further ado, if you don't have any other questions, I'll just continue with chapter 3, which you have already studied last week. And then in this particular chapter, the key thing that we really want to touch upon is 3.3, how to apply the least square criteria, and 3.4, choosing a best model. Here I want to further elaborate a little bit more for 3.4, how to choose the choose a best model, in the sense that for a business problem, especially for a problem that it's more like open-ended, and then you have to, as a modeler, you have to come up your own solution, and sometimes all the different modelers giving different solutions, and they are all working reasonably well, but occasionally it's not always the case. So I want to make sure that you understand when you're trying to build a model, it doesn't mean that the most complicated methodology that you pick will be the best. We always want to find the most efficient way. Maybe simple model would work sufficiently well. We don't want to go through complicated process. Just like last week, we mentioned that in certain cases we want to use mathematical modeling, but in some other cases you should be considering simulation. So apparently simulation itself is more complicated in terms of computational requirements. But in some cases, because the system is so complex, you don't really have a way to model it. You're left with no option but simulation. So in other words, if the system is really complicated and then have a lot of randomness that you have to build into the system, and different components work with each other dependently, and then you probably want to consider simulation. It happened that chapter 4 this week, we're talking about simulation, and then we're going to elaborate that a little bit more after this section. Here says 3 major tasks when we analyze a collection of data points. You fit in a selected model type or types to the data, and so you want to understand what would be the best model. In this case, you try to fit the model, and then next question is choose the most appropriate model from competing types that have been fitted. And you have to set up certain criteria to evaluate your model. And then after you use your performance metrics to evaluate your model, you want to use that model to make predictions from the selected data. And then in that case, you also need to set up criteria to determine how to make predictions. So I want to mention here a couple of things. Number one, when we build a model, one thing that we really need to do is called in-sample. So which is as the as the name indicates, what you do is you use your sample to build a model and then do in-sample analysis. It could be breakdown by individual variables that you analyzed and then look at the performance of your model on these individual dimensions. And then you would be able to evaluate how good this model is doing in the sample. Right? This is called in-sample analysis, but we're utilizing the whole full data set. And then in some other cases, you don't use the full data set. You use random selected 80% of the data and then leave off the other 20% off. In that case, you would do not only in sample of 80% of the data, but also the out-sample analysis of those 20% of data. And then it also comes to the next type of validation methodology that is called what we just said. It's just randomly select 80%. Right? There's another one would be instead of randomly select, you could be selecting based on time horizon. For example, if we're using last 10 years data, we have last 10 years data, we use last 9-year data to build a model and use the past recent 1-year data as a benchmark to test how good the model is. So that is also another type of outsample. And then the third approach that you can think of is also called cross-validation. So we actually studied some in the computational mathematics course. Hopefully you still remember, which is a variance and bias trade-off. You want to make sure that you are not overfitting in your data set itself. So here, the reason I want to mention this is just because this is other ways that you want to test to select your model. Of course, here we're talking about a criteria. What is the right criteria? Here we didn't really. If in this case, what I just mentioned for the example, it's really that could be the difference, right? Different error difference or absolute value of the error between the predicted value and the actual value, and sum them up. That would be one way, right? It could be the mean squared error. That's another way. So there are many other ways that you would be able to evaluate the model performance. So and then in terms of the sources of error in the modeling process, you could have formulation error, truncation error, runoff error, measurement error. Majority of the time, we're more concerned about formulation error. And of course, with the idea that we have sufficient trust or sufficient confidence in our data, if we know that there's some measurement error, sometimes it's very difficult for you to continue to analyze the data itself. And then visual fitting has potential pitfalls, as we know. It can't be perfect because you don't use certain criteria to evaluate how good the model itself. And then occasionally you have to do data transformation just because it may not be a linear relationship. After data transformation, you would be able to build a linear model. And then one of the models that's in the example on the figure 3.12, it says there's a chapter of approximation criteria, and then let's take a quick look there. I hope that you already read this section. If not, because for this course, if you do a lot of reading here by yourself, you would definitely see a lot of beneficial because it has a lot of mathematical details that we wouldn't be able to cover in 20 to 30 minutes of time frame for the whole chapter. That's why if you would be able to read, follow through, if you have any questions, definitely reach out to me and then we can discuss that together. Let's just quickly go through some of this, and then we would be able to get to the chapter of example rather shortly, right? So, and then how to fit this model. And interpolating the data using a smooth polynomial, this is just an example to see. And then the function form of the polynomial would be really y equal to c1 x squared plus c2x plus c3. And then you could fit in a parabola, and then you could try to fit this model. So you see that apparently sometimes we talk about extrapolation of the model, even though this model might fit really better, look like it's a perfect fit. We probably won't want to use figure 3.2 as the model itself. We would rather want to look at 3.3 as a model, as the candidate model. And then this type of errors I've mentioned. And then let's go to that example. So here this transformation is really trying to make it linear. If you use ln y as y prime and ln x as x prime, it is really y prime equals to ax prime. So it's a linear function in this case. Okay. So here, for this particular example, so we're trying to minimize this function form, and then yi is y equals to fx that minimizes this number. We're trying to figure out this function form, right? And then, for example, that suppose you want to measure the line segments AB, BC, and AC represented in above figure, and assume that the measurement yields the relation estimate AB 13, BC is 7, AC is 19. So apparently AB plus BC equals to 20, but your AC is really 19. So you know there is some sort of someone cannot hear anymore. Or? Oh, okay, that's okay. So it looks like you guys are okay, right? So here, AB plus BC is 30, but 20, but AC is really 19. So you should expect in any physical measurement process, discrepancy results sometimes do happen, right? So in this situation, the value of A, B, and B add up to 20 rather than the estimate AC equal to 19. Let's resolve the discrepancy of one unit using Chebyshev criteria. That is, we will assign the values to the three line segments in such a way that the largest absolute deviation between any corresponding pair of assigned and observed value is minimized. And then let's say that we assume the same degree of confidence in each measurement so that each measurement has equal weight. In that case, the discrepancy should be distributed equally. Discrepancy is a third, so that we can minus a third on AB and BC and plus 1/3 on the AC, so that we can make this relationship no more measurement error, right? So that each absolute deviation is 1/3, convincing yourself that reducing any of this deviation causing one of the other deviation to increase, so that we have this relationship. Formulates this problem symbolically. So let's say x1 represents the true value of the length of AB, and x2 is the true value of BC. Then for ease of our presentation, let's use R1, R2, R3 represent the discrepancy between the true measurement values as follows. So we know if AB is x1, we know x1 minus 13 is the difference. The true value minus your measurement is the discrepancy, right? So and then same thing, x2 would be x2 minus 7 would be R2, and then x1 plus x2 minus 19 would be R3. So earlier solution that we just went through says that let's distribute the error evenly so that we can get 1/3 in each segment. But here we're saying that let's minimize all these three errors. Minimize those. We're trying to find a value so that this is to minimize the largest of the three numbers. Okay, and then we say that we can let's call here. We say that if we call that the largest number is R, and then what we're trying to do is we're trying to minimize this R, and then correspondingly we can give some constraints to say, okay, absolute value of R1 less than or equal to R, absolute R2 less than or equal to R, so that we know R is the largest of the three absolute values, right? So in this case, we could further translate the problem to this function form because of the change the absolute value so that R1 is larger than or equal to negative R, less than or equal to R. And then question becomes as simple as this, because you're trying to minimize R and subject to certain conditions. And this we know that what we have already seen, if we put that this particular case, if we use R1 absolute value less than or equal to R, that can be replaced by R minus R1 larger than or equal to 0, or R plus R1 larger than or equal to 0. How do we get that? Based on this relationship that you saw here, you can separate this to two relationships, which would be R1 larger than or equal to negative R and R1 less than or equal to R. And then you do a little bit of manipulation, you would be able to say that R minus R1 larger than or equal to 0, or R plus R1 larger than or equal to 0. And then if this is done for each condition, we would be able to further to simplify further to represent the problem in the following form. That is R1 minus R minus this R1, which is defined as in the previous page, which is x1 minus 13. So in that case, you can replace that part and then to represent this condition. So now we have a set of linear functions that we can try to solve. This program itself is called linear program. And then we are going to discuss linear programming in Chapter 7, even though here we already talked about we use simplex method to solve this problem, and then the minimum value of R is 1/3, and next one is 12 2/3, and next 2 is 6 2/3. So which is different from the previous example that we get through if we evenly distributed them, right? So that's here, and then is it? I think it's actually the same. Oh, it is different. It is the same actually. It is the same. It happens that we evenly distribute gives us exactly the same solution. Apparently, it is different. And then here, give you a generalization of the problem that we just discussed, and then we have a homework on this. I was surprised that no one actually asked me how. In the question, it specifically asks that you can use simplex method to solve it, but apparently you haven't learned simplex method yet. And then if you don't know how to solve it, you can just leave it there, stating that I haven't learned simplex, I wouldn't be able to solve it, or you can even just figure out some other solutions that you would be able to solve. But I'm going to go through that example next time in terms of the homework once I publish the solution, and then we can discuss further on that aspect. So that's a detailed discussion of this example, and then it's something that rather interesting that we start with a math formula, we translate it to a linear program. Linear program, by definition, is linear objective function and the linear constraints. And then apparently the data actually have other examples, generalization of this problem, and how we can continue with that aspect. And then if we take a look at next question that we are going to discuss, that is the sum of least squares of error. Okay, for the sum of least squares criteria, Okay, so what we're doing here, let me go back there. So what we're trying to do is, if we use the same notation shown earlier, the problem is determine the parameters of the function form of y equal to fx to minimize the sum of yi is the observation value and fxi is your predicted value. So your observation minus the predicted value, absolute difference squared, and then sum through all of the individual i's. So in that case, this is your objective function, and the question is, how can we solve this type of problem? And then I just want to quickly mention that what you can do is, apparently it's a quadratic function, and in order to get the minimum or maximum, you should formulate the least square. If formulate the least square and take partial derivative, and then set first order partial derivative equal to 0, you can solve for slope and intercept. Meanwhile, what you do is you take the second order derivative so that you would figure out its minimum or maximum value, right? If its second order derivative is larger than 0, then you know you find a minimum value, and then if your second order derivative is a negative value less than 0, then you know that you find a maximum value. And so here I just want to say that for linear regression itself is objective function is really this least square problem. You use your you're trying to minimize the error of your model comparing to the observed value. And then hopefully this piece you actually get a sense already. If not, I was thinking if, let me see if there's some picture that would be able to help me to explain this a little bit better. Okay, this theta straight line, how we can get this, and how do we use this, and trying to take the first order derivative, set them to 0, and then trying to solve A and B, slope and the intercept. That's that. And then apparently there's some transformation that helps you to simplify the problem. And then there's some third order, fourth order type of problems that you can further transformation as well. Now we go to 3.4, which is choosing the first order of a best model. So you look at the fitting error, you compare different models, you think about the error term, the complexity of the model, whether the model is having a overfitting issue I already mentioned earlier, and whether the model itself has any generalization capability. And then you would be able to explain you would be able to pick the best model. In other words, it's a consideration of all these aspects, not necessarily the smallest error would be the best model. And not necessarily always mean that most complex model would be the best model. On the other hand, majority of the time, we would rather say that the most simple model and the effective model would be the best model. So that was the homework for last week. This is unit 3. I was okay. Yeah, here's yeah. Continue with this. I want to say that last week we actually have a lot of assigned questions. You only need to pick 3 out of those 2 chapters. One of the reasons is because those 2 chapters in general have very similar ideas, and especially chapter 3, relatively speaking, it's straightforward. So let's continue with chapter 4, and also we have to discuss a little bit about chapter 5 today as well, because it's simulation, it's introduction, and then majority of you probably is taking a more deep dive of the simulation, so it's really not, hopefully it's not new for you for chapter 5 as well. But in chapter 6, 2 weeks from now, would, 2 weeks from now, you would be really, which is next week actually, you need to read the chapter 6, which is linear programming simplex method. That would be definitely new for many of you. And then so let's look at chapter 4. So it's really just trying to give you some idea of higher order polynomial or cubic spline models, how those models can fit into the data itself. And then as I mentioned earlier, we don't really want to choose C, but we would rather choose B in this case because it probably have better generalization capabilities. And then we have to consider transformation and ladder of the powers. Some of the transformations we started considering majority of the time. We kind of go through this and try different possibilities and figure out the best transformation for your data. If you have done a little bit homework, you would know exactly what I meant here. And then different transformation probably have different perspective or different fit for the model. In this case, actually, in general, all those 3 transformations is doing a reasonably well job. Okay, this is interesting that we introduce a new thing. It's called Lagrangian form of the polynomial, which is based on the initial observation of the data you want to fit this unique polynomial of at most degree n with a property, this certain property, and this polynomial is given by the 4.3, this particular function form. And then Lagrangian is one of the methods in nonlinear programming, and then we actually would touch upon, come back on this concept in somewhere in week 10 or week 11, and then we can discuss a little bit further. And then mention that, as mentioned, we should have all these considerations, and low order polynomials, it probably don't have a lot of, it probably would have a lot of error in terms of the fit, and then complexity of the problem of the model is rather not that complicated, right? And then potential of overfitting of the problem model is not that high. And then generalization of the model is better for the low order of polynomials. But on the other end, if you have a high order of polynomials, you probably have less error, but your model is more complex, and then you have a potential of overfitting problem, and it has less generalization capability if you have a higher order polynomial. So that gives you a sense of which model you probably would be able to take a look. I mean, to pick. And then linear splines is also called piecewise linear functions. Or in many of the modeling exercise, especially in real work, you probably meet a lot of this type of analysis. You use piecewise, separate those fits into pieces, and then estimate each individual piece separately. And then you can also do cubic splines, which is the graph on the right-hand side, and to fit the data. So you can say that for those 3 data points, you already have 2 ways to fit those model, fit those data. And then this is the homework for chapter 4, and you can pick 3 out of this. So continue with what we're trying to cover for week 4. And then what we do is we talk about simulation. The data has, the book has further detail here. I'm going to lead you through. Hopefully you would be able to read pieces on your own. I'm going to try to explain the most difficult sections that I see in this chapter, and then you would be able to understand better. So for the first section, it was trying to introduce how to simulate deterministic behavior. For example, area under a curve, and then in one of the homework, we're trying to estimate the value of pi based on simulation, the pi that you use to calculate the area of a circle. So that's definitely used in many cases. And then the second section we're trying to explain here is how to generate a set of random variables, random numbers, and then how do you use those generated random numbers to simulate probabilistic behavior in 5.3, and then in 5.4 and 5.5, they are really the applications of the simulation model, even though for queuing models itself, it has a specific subset of mathematics that's called Markov chain models. In Markov chain models, I actually have an example in the week 5 material. So if you're interested in that, you should definitely go there and review those material. And then just for your information, for many of the retail store type of checkout counters, we use queuing models to analyze those behavior of the checkout counters, so that mathematically you could use all this queuing type of approach to analyze what would be the best number of checkout counters for target, for example. That would be a business question that we could answer. And apparently for this type of problems, you would be able to answer the question using a simulation as well. And then similar type of problems, including how you do analyze the efficiency of a specific intersection, for example. It's the same thing as a queue and trying to analyze how much you would be able to, how much green light time that you would be able to give to the system, so that for a specific direction, so that the queue would be the function of the intersection or the signal light is better, it's more efficient. So that's the idea, to give you a sense on what we're talking about here. And so if we talk about last week, just now, 20 minutes ago, I already mentioned what's the rationale for using simulation models. When in the case that you are not able to construct an analytic model, and you wouldn't be adequately explaining the behavior observed, and then you have to do simulation. But on the other hand, simulation to obtain some data, you would be able to do further analysis. And then in many cases, if alternative procedures need to be tested, may not exist, the only thing that you can do you are left with is a simulation. So so on the left hand side, you see that behavior could be deterministic and the model can be deterministic or probabilistic. On the other end, the behavior could be probabilistic and the model could be deterministic or probabilistic as well. So let's move along. So here, let's take like a minute break. I'll just get some water, and then we can continue this section, which is how to simulate the deterministic behavior. Just hold on, just hang on there with me for another 30 seconds to a minute. Okay, so let's continue with this example. So assume that you have this function form, and what you're trying to do is the area under the curve. So one way that you can think about it is I just randomly throw points into that square boxes, and then what percentage of the points actually is underneath the curve, right? So we can throw in 10,000 points, turns out to be 400,000. 10,000 points turns out to be 4,000 of them below the curve. Then we use that 4,000 divided by the 10,000, we get the area under the curve is probably 0.4, assuming that the square box, the rectangle has the area 1, right? That's the basic idea of how to simulate deterministic behavior. Apparently that you can see that there is a complication here, potential complication here. We are assuming that the probability of going to any data points is equal. In other words, the weight itself for throwing that dice and it's landed somewhere, that probability is the same. This is a simplified assumption, but apparently for this particular example, it's sufficient. We don't really need to consider further detail, but in many other cases, you might want to consider how to embed that probability into that probability or that weight into the equation to calculate your area on the curve. So, and then this methodology itself is actually rather simple, and its only difference there is different from what I just said was I was saying that we have a unit of one unit of the square area of the square, but here it's even better to say that xi is between a and b, yi is between 0 and m, so that you know your area is really m times b minus a. That's your area of this square, and then you use your counter divided by n times this n times b minus a is really the area that you're trying to calculate. That's one of the examples. Deterministic behavior, how to simulate, and it's rather simple, right? So if you have any questions in between, feel free to ask. So and with the extension, saying that instead of 2-dimension, what if it's 3-dimension? And the idea is essentially the same. Volume on the surface divided by volume of box roughly equals to number of points counted below surface in first octant divided by total number of points. And next step that we discussed, how to generate a set of random numbers. One of the methods that we came up that we usually use is called middle square method. So you start with a 4-digit number x0 called state. The first number from your simulation is always called a seed, x0. And then in this case, this particular method says square is to obtain an 8-digit number and add a leading 0 if necessary. If you don't really have the 8-digit, if you start with 300 and then powered by, you square it, you get 90,000, right? It's still not 8 digits. You can add leading zeros, and then what you do is pick the middle 4 digits of your next random number, and then continue with that. Sorry, my example was flawed because the first number that I just let you guys know was 300. Should be 3,000, right? Because we start with the 4-digit number. So if you continue with that, for the third step, you get the middle 4 digits as the next random number. Continue with that, and then at the end, you would be able to see all the random numbers that you generated. And then in the exercise that we have, in the homework, we say, okay, let's study some certain behaviors. As you probably realize, in some of them, it starts cycle rather quickly. Instead of after 10 iteration, you realize that the 11 number is the same as the first number. So this type of random number generator is apparently not that random, right? If you could potentially be cycling every 10 numbers, it's very dangerous, right? If you want to do simulation, you need a real, we call it pseudo-random number, because it's not real random, but it's sufficiently random enough so that you have a very long sequence before it goes to cycle, which is another method that we actually have, we'll touch upon, which is called LCG. I think we're going to talk about it. That model itself usually have a reasonably long cycle, which is more ideal in order to do your simulation. Okay, so this is method 1, and apparently this is the second number that I was going to mention, which is LCG. I just said probably the wrong term, linear congruence generator, which is based on xn, you can times a plus b and mod c. C is the modulus, A is the multiplier, and b is the increment. And based on xn, you can get xn plus 1, xn plus 2, etc., etc. And pay attention to possibility of cycling, lack of statistical independence among members of the base of random numbers. And apparently we say pay attention to, meaning we are trying to avoid the possibility of those two cases. And you would rather to have a pseudo-random number, and you don't want, if your random number are not random, what could be the potential problem? Potential problem would be you're thinking that you are analyzing the different behavior of the system. It's really the way that your random number is not generated that well made you think this behavior is real. But the reality could be that just because the random number is not so random, the behavior are false alarmed. So that's the reason we don't really want to have this happen. And then we discussed how to simulate probabilistic behavior, and then simple probabilistic models. You flip a fair coin, you roll a fair die, or roll an unfair die, or a pair of unfair dice, and then you can estimate the probability based on simulation. And then let's use a fair coin as an example. We always see that mental color simulation. Apparently, this would be one of the examples to be considered as mental color simulation. The total number n of random flips of a fair coin to be generated in the simulation, and the output is the probability of getting ahead when you flip a fair coin. And the initialize count is 0 for every single step from 1 to n. You go through step 3 and step 4. Step 3 is to obtain a random number xi between 0 and 1. So it's very, in R, for example, you can easily just use rand to generate that random number. And you can use 0 to 1 as your boundary so that you would be able to generate that 0 to 1 random variable. And then you just, if x is between 0 to 0.5, you use counter equal to counter plus 1, because you know it's a fair coin, so that the probability that you have a head, the flip of shows up as a head is 0.5. Otherwise, you just leave the counter as is, and then you can calculate the probability of head equals to counter divided by all the nth rows, right? So that's your probabilistic behavior simulation. It's rather simple as well if you think about what we just discussed earlier for the deterministic. They do have very much similarity and interesting things together. So what about a fair dice? Only difference is instead of a probability of a half, it's a probability of 1/6. And we have examples, homeworks on this question as well, and definitely go through them. Interesting problems. What if it's unfair? We see that you have a probability of, just different probability, right? The first is around 0.1, second one is interval is 0.1, the third one is really 0.2, the fourth one is 0.6. So in that case, you can, in certain case, you increase your counter of I, counter 1 could be counter 3, could be counter 5, depending on the random variable that you actually get. And then you can calculate the probability of different counter, meaning that the probability of each row being 1 to 6 as corresponding counter of 1 to 6 divided by n. You can get your probability of each row. And then in the inventory model, that as an example in the textbook, it's just give you a sense that how to analyze the average daily cost with the potential variables that you want to consider, storage cost, delivery cost, demand rate, and some other fixed costs, etc. And then with a certain level and frequency of demand level, how you can analyze the average daily cost. It's called inventory model. It's widely used in many of the distributors, such as online distributors, such as Amazon or eBay, or these firms would have a question on inventory. And then people have to have certain trade-off between the inventory cost and the lost sale cost. You don't want to stock too much, but on the other hand, you don't want to stock too little, and potentially you wouldn't be able to satisfy the customer demand, and then you have a lost sale, and it's going to be a loss for the firm. And then the book has more detailed example, even though if you are interested, definitely go through that. So for example, what's your next inventory cycle be, because you have an initial inventory to start, and then you have a quantity that you try to order a certain demand. So your new inventory would be inventory equals previous inventory plus Q, and then your customer would be C equal to C plus D, that's the coming demand, etc. And then in certain threshold, when you actually reach certain threshold, you are trying to reorder or stock out, and you do analysis, calculate your average daily cost, and then to determine what would be the right stock level. And then for Q model, here I want to so I want to discuss a little bit just that. For example, in a Hubble system, you can see in the pieces that the system is very complex to be modeled, but analytical model simulation can help quite a bit. And also, it could be the case that subsystem might be modeled using analytical methods, but the overall complicated system are still using simulation. Some sub-components are analytical models. So review the example that I have on the textbook. In the week 5 material, I'm going to go through that rather quickly as well. And then some other models mentioned earlier, morning rush hour, multiple server queues, and this can be used supermarkets to estimate how many servers checkout booths should be needed as well. This is a homework, and let's go to the course page. Hold on, I have, yeah. Let's go to the weekly materials. Okay, it's probably already. Oh, okay. Oh, no, it's not here. The way I'm looking for my queuing example. I think it's probably in section 5. Yes. It happened that I should move this section to week 4. It's really should be in week 4, which is this Markov chain examples. And then you should be taking a look at this. Even though it has connection between week 4 and week 5, and then I put week 5. There was a reason that it's there, just because we're doing probabilistic models in week 4, but a week 5. But on the other end, for week 4, we do have this queuing models that is using the Markov chain. So you should review them either this week or next week. That would be helpful for you to understand the queuing systems. There's some YouTube videos for the queuing. Hopefully that helps. That would be helpful. So that's pretty much that I plan to cover for today. If you have any questions, you can ask now. Logistic-wise, cost-wise, anything. We require to use R for every question. It's not quite right. So, for example, let me give you another example. It happened. Hopefully, I still open it. No, I don't have the book on top of my head, but not necessarily, because for some of the derivation, for example, second order derivative, calculate A and B, etc., you don't really need to use R to do it. You just use your equation and do the calculation, you get the value. That's it, right? But so for some other things, program-wise, you need to write certain program to help you to answer the question. Yes, please use R if you could. Page 194. Hold on. Give me some time. I can navigate to that page. Okay. 194. For which question? Question 1. I think you could, because it's only 10, apparently you can use. I don't see any reason that you use it manually. You probably use Excel or any even your calculator. But apparently it's ideal to use R because here it's asking for 10. What if we're asking for 1,000, right? But for me, in terms of summation, if you manually calculate them, I'm fine with that as well. Okay. Any other questions? No. Okay. If you don't have any other questions, we can stop here. Ask me questions offline through email if you have any on the textbook. Again, I hope you would be able to read the textbook. It would be much more beneficial for you at the end of a semester. If you read the whole book, you would realize you learned quite a lot. If you only just based on whatever I'm trying to teach you in an hour for 2 weeks, and then you do the homework, you don't learn as much. In my opinion, whether you do the homework or not is less crucial, but whether you read the textbook or not is much more crucial. Okay, that's it for today, and then I will see you in 2 weeks. And next week I will have my office hour starting at 8. And if you have questions, feel free to join me. Thank you. Have a good night.